Last session was primarily focused on using methods to estimate the thermophysical properties, और उसमें analysis was very limited. So to be honest, उसमें सिर्फ pure component का एक analysis feature properly use किया था. Otherwise for the binary system we ended up taking the experimental data from NIST Thermo Data Engine and try to simulate the same data using two different methods. One was NRTL. NRTL is the activity coefficient model, and the method is the same NRTL, where other equations to estimate different transport properties are clamped together to make it a complete method. So the example is, if we have a 70% methanol and 30% chloroform, that again makes the azeotrope, because visualization of this mixture is even better than visualization of ethanol water system. For that purpose I just had taken this example. Still we can use the other ethanol water system as well. So the mixture forms azeotrope at 35% methanol, and remaining 65% should be the chloroform. That is the azeotropic point and ambient conditions. So at ambient conditions, if we are working with the distillation, we cannot get beyond this composition. How can we do? We can work with the different pressures, and since pressure deviates the azeotropic compositions, so that concept, principally that concept can be used to develop high composition methanol or chloroform. So having this system, the question is, perform Txy analysis at varying pressures to identify the shift of azeotropic composition, and conceptually develop a process for pressure swing distillation using binary mixture Txy analysis. So we are asked to just have a conceptual layout of the distillation, and that is a pressure swing distillation. So let's get into Aspen Plus and see how we can use binary analysis feature to work on this example. Okay, should we continue? Okay, let's focus. Let's create a new simulation. We are not interested in selection of any default template. Let's create a new simulation. So two components are methanol and chloroform. So you can directly search methanol and chloroform. Let's see if we can search like this, chloroform. So we cannot search chloroform a complete ID from here, because this ID is limited to 8 characters. We can search from the component name. This is not limited by any number of characters. So you can search from here, chloroform. Yeah, it extracted chloroform from the database and the case number is given, but ID is missing. You can give any ID. Let's say chloro. Okay, so we have two systems. Then we need to define the thermophysical property method. Either you can click next, or you can go to the navigation pane under method. Wherever there is a half red circle, that means that's a page where you need to define something. Here let's try with the NRTL method. So after defining NRTL method, we need to review the binary parameters. So you can go to half red circles, or you can click next to this page. So it's just to review this. So that's it. We have defined everything and we are ready to perform the binary analysis. So we are not going to fetch the experimental data once again. Let's directly jump into the binary analysis. Okay, either you can click from here from the analysis tab, or you can directly create from the analysis. So we are on this page. Everybody on this page? Yeah. Okay, so we were asked to do the Txy analysis. So analysis type is fine. We need to define two components. That's already selected. If there were multiple components, then you had to be very much sure we are on the same page. For the Txy, the x-axis is always the liquid and vapor composition, and y-axis is always temperature. So the manipulated variable is liquid composition, and liquid composition or the vapor composition varies from 0 to 1, and we are talking about the 50 intervals. Here you can define the pressures as many as you want. Right now we have only one pressure, 1 atmospheric. Let's run the analysis. Okay, so this is methanol chloroform behavior at ambient conditions. Okay, so now you can identify the composition. The x-axis is manipulated variable is the composition of methanol, and with the example we had 70% methanol. So that means we are talking about the point somewhere here, this one 70%. So from 70%, can you identify which is the liquid line and which is the vapor line? The green one or the blue one? Which is the liquid one? Blue one. Yeah, with the X composition, that is the liquid, and the green one is the vapor composition. So if we want to perform the distillation in this region, again the higher temperature is close to the pure methanol, and you can identify the exact value over there. If you want to cross check the number, what exactly is the number, so you can activate the tracker. So you can right click anywhere on the window and show the tracker. So with the tracker, wherever you move on the same curve, it will give exactly the indication of the numbers. So if you go all the way to the right, you can read the numbers. So the Y number, mean the y-axis value is 64.5, that is boiling point of methanol at ambient conditions, and the composition is 1 over there. So if you move along, if you put this mixture 70% methanol in the distillation column, doesn't matter how many number of stages are you talking about, you will have two extreme conditions. One is in the boiler, reboiler, and other one is in the condenser. The condenser operates at lower temperature throughout the column, and the reboiler operates at highest temperature inside the column. You can read the extreme conditions. The higher one was 64 point something, and the minimum is just at the azeotropic condition, and the azeotropic conditions are around 35% methanol composition. So you can read the temperature 53 degrees Celsius. So if we operate the distillation column, can you identify what should be the composition in the condenser? (35% methanol), yeah, in the condenser. And the reboiler will be high temperature pure methanol. We cannot go beyond this composition from the azeotropic composition. What if we have the multiple curves, mean Txy multiple curves at different pressures? So let's try, if we have other pressure condition, can we move beyond this composition? So for that purpose, go to the analysis feature, again under the binary one we were working on, and here you can add as many pressures as you want. Let's put a different pressure, 5 or 10, let's take 10 bar. You just need to enter the value, and we are with the units of bar. You can run the analysis once again. Just click run analysis. Okay, so in this analysis, the lower one is at 1 bar, the upper one is at 10 bar. So initially we were working in this region, yeah, on the right side. So we ended up with around 35% composition of methanol in the condenser. If you just see at higher pressure right above this composition, and we are way beyond the azeotropic composition. This region, again this region is a two-phase region. So at the same composition, just raising the pressure beyond 1 bar, we are again in the two-phase region. So right over here in this region. So in this region, the azeotropic composition lies on the right side. You can read the azeotropic composition. So it will be somewhere here. You can show the tracker. So the azeotropic composition will be something like 56% methanol and the remaining chloroform. Previously it was 35% methanol for the azeotrope. Now the azeotrope is beyond 35% and close to 56%. So that means we can rework the distillation process for this two-phase mixture, and we can again get one product from the reboiler and one product from the condenser. So can you guess, if we are talking about another distillation column, what should be the temperature of reboiler and what should be the temperature of condenser? Can you read it from this graph? So the high temperature around 153 degrees Celsius, that should be in the reboiler, and the lower temperature is something like 130 degrees Celsius, that should be in the condenser. So for the second distillation column, if we feed the first azeotrope, pump it to the 10 bar pressure, then feed it to the second distillation column, operate the column, and in the condenser we will get another azeotrope with the higher composition of methanol, and in the reboiler we will get almost pure chloroform. So this is how we can trick with the azeotropic composition, just installing a higher pressure device inside the two columns, and we can work with this azeotropic distillation and get almost pure components, one in the first column and the other pure component in the second column. So this is how we can use this binary Txy analysis and conceptually develop a flow diagram that can be used to generate pure compositions beyond the azeotropic points. So this condenser product from the second column or the distillate, it's at higher pressure. We can reintroduce this composition back to the first column. We just need to drop its pressure back to the operational pressure of the first column and introduce it in the first column. So that will be a closed loop between the two columns, first operating at a lower pressure, then generate the pressure to higher pressure. Second column will be operating at a higher pressure. When the products are obtained from the two reboilers at different products, then we can reduce the pressure from the second column and reintroduce in the first column. So that gives a very conceptual scheme of playing with the azeotropic mixtures to get the pure composition, and this is what we term as pressure swing distillation. So one conceptual flow is given in this figure, and that is available in the handouts. So here we have the feed with the 70% methanol and 30% chloroform. Get the distillation from the reboiler, we can get methanol, and from the condenser again we can get azeotrope, that is azeotrope at 1 bar or the ambient conditions. Pressurize this, change the azeotropic composition with the increase in the pressure, get to the second column, operate this column, and again from the second column we can get almost pure chloroform from the reboiler, and the azeotrope at 10 bar, that is close to 56% methanol, and that azeotrope is from the condenser of the second column. Then we can make a closed loop by reducing the pressure back to the operational pressure of the first column. So this is how we can work with the pressure swing distillation, and this binary analysis or the Txy analysis at different pressure helps to design such kind of operational schemes. Everybody got it? So at least for the binary analysis, we can first judge whether the thermodynamic method is suitable for that system, and that can be checked by comparing the experimental data obtained from the NIST thermodata engine with the simulated data, and we can perform the simulation with lots of different methods and just cross check with. If the simulation mimics the actual behavior of the experiment, that means that thermodynamic method can at least mimic the two-phase behavior, and that is appropriate for the given system. And the second is, if we have the azeotropic system, we can play with the different pressure, perform the analysis, and from that analysis we can conceptually develop a kind of schemes that can help treat the azeotropic compositions and perform the separation process. So what should be the minimum pressure to shift the azeotrope? That again can be checked from here. So if we perform the analysis at even a different pressure, so if we have another, let's say at 5 bar, we can just enter a 5 bar in the same chart and run the analysis once again. So the middle one is the Txy at 5 bar. So again, the first azeotrope at 1 bar was around 35% methanol. Just go to the 5 bar at the same composition. Still this phase is in the two-phase region. So that means even you operate at 5 bar, that will reduce the cost of the reboiler and the condenser of the second column as well. Also it will reduce the energy requirement for the pump as well. Still you can appropriately work with the distillation operation. So that way you can try different pressures. In the upcoming sessions we will be in the simulation environment, and we will work on the same example or the similar example once again, and try to do the sensitivity analysis. What should be the minimum pressure at which the second column should be operated in such a way we can work with the different azeotropic composition to get the pure components from the azeotropic mixtures. So this is how conceptually it works. But this is not the only thing. At the same time, if we are reducing the pressure, we can favorably enter into the two-phase region crossing the azeotropic composition. But if we operate the second column at a lower pressure, whether the second column design or the geometry will be the same as it should be operated at a higher pressure? There are lots of other variables. How many number of stages should be there? What should be the reflux ratio or the boil-up ratio in the reboiler? Those are other variables. So this is a very general scheme. The decision lies what should be the geometry of the column 1 and the geometry of the column 2, what should be the overall cost required by the energy. That whole picture at different sensitivities give a clear picture what should be the conditions, operational conditions of the two columns. That gives let's say minimum any economic indicators. For example, what should be the minimum rate of return while working with this complete system. So that economic indicator can give a final decision indications what should be the operational regimes of the two distillation columns. So the trade-off between the two columns and the operational conditions will give the final answer what should be the exact geometry and the operational conditions for the two columns. Okay, so this is all about the binary analysis. Anything you want to add from here, or we can jump to the next analysis? All right. So then we have distillation synthesis analysis. Let's move from 2 components to 3 components. This distillation synthesis analysis, that's a feature that is very commonly used to analyze the ternary systems, especially to perform the not the pressure swing distillations, but where we can introduce a liquid extraction system. This is a very powerful tool, to be very honest. This distillation synthesis analysis, that's a very powerful tool. So there are a couple of terms, since we are working with the azeotrope, with the liquid extraction process, with the Ternary diagram. So that means there are multiple terms that we need to realize even before jumping into the actual exercise. So let me know if you are not aware of any of these terms, because we have to use them. Ternary diagram, So that's a diagram drawn between three components, preferably for those components that make different liquid phases. Azeotrope, we are fully aware of this term. Homogeneous azeotrope and heterogeneous azeotrope. Any doubt in these terms? One, we are talking only in one liquid phase, and the other azeotrope is when we have the multiple liquid phases, that is heterogeneous. Then there are stable nodes, saddle. These are two different nodes. Stable node is a composition point on the residue curve. We are talking about another term, that is a residue curve. So what is the residue curve? Residue curve is a trajectory on a Ternary diagram, again on the Ternary diagram, showing how the composition of the remaining liquid changes during the simple distillation process. So if we have a Ternary system in a single liquid phase, and we operate a distillation for that single liquid phase, how the liquid in the reboiler and the vapor in the condenser, those compositions vary at different temperatures, or at least the line connecting these two composition between condenser and the reboiler, that line is the residue curve. So that means whenever we are talking about the residue curve, we are talking about the distillation process, and whenever we are talking about the liquid extraction process, that is the tie line. So tie line connects the two separable phases in the liquid extraction process, that is the tie line. So one is the raffinate, the other one is extract. How do we call it? Extract. Okay. So those two compositions, they are connected by a single line in the liquid envelope. Those are the tie lines. So stable nodes are on the residue curves, and the saddles. Composition points on the residue curve make that neither attracts nor repels other curves, indicating an intermediate separation state. So that is in between the stable nodes that we call the saddles. Then there is a plate point. Plate point is the single point. This is similar to the critical point in the vapor liquid equilibrium curves, but here the plate point is related to the liquid process. So when all the tie lines converge to a single point that is not separable by liquid extraction anymore, that is the plate point. And then there are envelopes. We have one liquid envelope and one vapor liquid envelope. So these are the regions. In fact, inside the Ternary diagrams, these are the regions that we term as envelopes. So once you are good with these terms, then let's do this exercise. And the exercise is an equimolar ternary mixture of ethyl acetate, ethanol and water. So ethanol and water common with the previous sessions, and we are now having a third agent, that is ethyl acetate, and we are talking about 1 bar, and that forms azeotropes in the homogeneous and heterogeneous regions, and those azeotropes make it impossible to achieve high purity ethyl acetate using simple distillation. That's true. One possibility is to use a combination of distillation and liquid extraction to achieve high purity ethyl acetate. So if there is a mixture of ethyl acetate and ethanol, that makes azeotrope as well. If that is the azeotrope, we cannot get the pure ethanol and the ethyl acetate from the same distillation process. Either you can operate with the pressure swing distillation, or you can introduce water as a solvent, and that solvent will preferably dissolve one of the component and leave the other one to get into the second distillation process and get the pure distillation. So we are asked to analyze the system using an RTL HOC model and conceptually design a separation process. So with so much discussion, can you just picturize what could be the possible scheme for this ternary mixture? We have the equimolar ternary mixture of ethyl acetate, ethanol and water, and we are asked to get to a pure ethyl acetate, and we have to develop some separation scheme for that process. Can you just before analyzing the system, conceptually develop what kind of separation scheme that could be? So we can work with the distillation as far as azeotrope is either in the boiler or in the condenser. We can work in between those regions, and the residue curve will help us to identify where should be the azeotrope and where should be the other component. Then once the azeotrope is performed, either we can switch to the pressure swing, or we can work with the addition of other solvent or addition of one of these components as a solvent that will move the azeotrope from its original composition to another composition. Possibly if it lies in the liquid envelope or a region where we can have a liquid process, then we can work with the liquid extraction again to get two products, one as a raffinate and the other as an extract, and then we can rework from those products and get the distillation to get the pure ethyl acetate. So this is how the conceptual framework should be. But let's analyze this system and see what kind of response is it and what kind of compositions we can get. So let's get back to the same example. We can just remove the components, unrequired components. Both are not required. You can just select individually from the left side where the small arrow is there, and you can right click and delete this row. Or even if we want to have the ethanol, you can write it exactly on the ID and hit enter. It will gives a pop-up either to replace just the ID or delete the component. If you delete the component, exactly it will fetch a new component that is named as a new ID. So this is another way to do the same thing. So we have ethanol, water, and ethyl acetate. For ethyl acetate, we can enter in the component name. Ethyl acetate, it got to the find component window. You can pick the criteria equal to, that will at least reduce the number of search results, and then find now. Okay, so there is only one component with the name ethyl acetate, exactly ethyl acetate. You can add the selected component to the component list. So I prefer to rename it as per my convenience. Let's say I name it E space acetate, E dash acetate. You can name anything you want. So we have three components. Next we need to replace the NRTL method. From NRTL to NRTL HOC. Before moving to NRTL, just read what is the vapor equation of state for this system, for this method. ESIG, that is equation of state ideal gas. So NRTL method assumes liquid activity coefficients, but for the vapor phase it takes ideal gas equation of state. But if we replace it with the NRTL HOC, so again the liquid phase is defined by the NRTL method, but the vapor phase is defined by the HOC equation of state. So that's a big difference between simple NRTL method and NRTL HOC. There is another option, NRTL RK, that is also commonly used. RK is the Redlich-Fonck equation of state. So if we choose this NRTL RK, that means the liquid phase is still treated with the NRTL method, activity coefficient method, but the vapor phase will be treated by equation of state. That is not the ideal gas equation of state. So any non-ideality in the vapor phase will not be reflected by simple NRTL method, but rather if you use the variation of NRTL, then it can be reflected appropriately. So NRTL HOC, let's see what other windows it pops up. HOC and some binary interaction parameters. So just one thing another to add, sometimes if we have a multiple component system in the component list, quite possible all binary mixtures are not reflected in this page. This page is under the method, under binding direction parameter, and in the NRTL. This is common almost for all activity coefficient based methods. Let's say if even one of the mixture is not over here, that means that mixture will not be incorporated by activity coefficient method, because we don't have any information of the molecular interactions between these two components. So just make sure all the possible combinations, binding combinations of the given are the components of interest are in this list. If there are not, for only 2 components we had only 1 binding mixture. For 3 components we have 3 possible binding mixtures. So that means 3 rows should be here. If for any exercise you are dealing with this is not true, then one possible option is estimate the missing binding interaction parameters using UNIFAC method. So if we just need to click this small checkbox. Be very much careful when dealing with such kind of system. At least some information is better than having no information at all. So the minimum information we can get is from the functional groups interactions, and that is captured by the UNIFAC method. So when this box is checked, all the possible combinations will appear under this window. If it's stuck somewhere, you just need to wait for some time. You just need to wait give some time to the processor, it will get back. So if any time Aspen Plus is taking some time to show the results, don't click anywhere, otherwise it minds it. Okay, so that's all to introduce the binding interaction parameters, ensuring that all the possible binding pairs have the binding interaction parameters. Okay, then there is a half right circle for the binding interaction for the binding analysis. We don't need to work on this. Just click on the analysis folder, not under the analysis, on the analysis, and you have the cross button over here. You can simply delete it because we don't need it. It's just creating a mess for us. So we have a very clean window, and the required property inputs are complete. That means we can run this simulation. It will just fetch all the properties and estimate the remaining properties. It won't show up any result as of now, but it will do its background work. So once this is done, now we have to enter the distillation synthesis analysis. And the distillation synthesis analysis, this is under these 2 options, Ternary diagram and the residue curves. So let's enter the residue curve. Enter this, a small window pops up with the 4 different options. For the help, the first option, the second option is if we are only interested to see how many azeotropes are found in this ternary system. The third one is we actually want to use this distillation synthesis analysis, and the fourth one is if we are only interested in the residue curves. So the distillation synthesis analysis, it includes the search of azeotropes, it includes the residue curves, it includes the ternary diagrams, and all the elements of the ternary diagram. So the third option, distillation synthesis, is the most comprehensive out of all these options. Even it includes the other option in the analysis, the ternary diagram. So that ternary diagram is by default in this distillation synthesis. So just enter the use distillation synthesis ternary maps. Use this option. So we land in this option. How to use this option? Just see, this is one navigation pane. This is specific to this distillation synthesis analysis. The first option is to introduce all the inputs. Then there is all option of outputs, where we have the information of the azeotropes as well as the information of a complete report. Then there is option of ternary plot. Yeah, these are multiple options. We'll navigate between these options. But on the working window, the first information is introducing the components. Since we have only 3 components, so 3 components are there. Then the operational pressure for the analysis. On the right side, we have different methods for the vapor liquid equilibrium and liquid liquid equilibrium. You can play with these methods as well. You can choose another method for the vapor liquid and other method for the liquid liquid equilibrium. By default, if you are doing the Ternary analysis, just check this second option, vapor liquid liquid equilibrium. If this is only vapor liquid equilibrium, that means the required liquid equilibrium will not be calculated and will not be shown. So choose the 3 phases in this. Then you can select the basis, mass or mole, temperature units, and on the left bottom we have the options to calculate residue curves, azeotropes, and the distillation boundaries. So keep all these 3 options checked. As of now, we don't need to work on this because we have operation at 1 bar condition and 1 bar is almost there. Just enter the azeotrope option on the left, azeotropes. That should be the first point of interest. How many azeotropes are formed and what is the nature of those azeotropes? Here we have 4 azeotropes in this system. Just see the type of azeotrope: homogeneous, 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 and heterogeneous. So 3 azeotropes are homogeneous, that means they lie in the single phase, and the one is the heterogeneous, that means here we are talking about the liquid liquid, 2 phases existing at the same point. 2 different liquids mean 2 different phases, and phase is exactly the homogeneous one. So other homogeneous phase is another phase. Then you can see the composition and corresponding temperature for those azeotropes as well. For example, the first azeotrope between 88% ethanol and 11% water, that occurs at 78 degrees Celsius at 1 bar. So similarly, you can see 70 degrees Celsius azeotrope is between ethanol and water and ethyl acetate. So 3 components are in the azeotropic mixed form, but still this is not the heterogeneous one. They are on the same phase. The heterogeneous one is made at 71.39 degrees Celsius, that is only between water and ethyl acetate. So ethyl acetate makes an organic phase, water makes an aqueous phase, so these are 2 different phases and they are still in the azeotropic composition. So that is a heterogeneous composition. Okay, so if you want to show all the components including the pure components, then there is a third option, singular points. Singular points list all the pure components and the azeotropes as well. So we have 3 pure components and 4 azeotropes, that means there are total 7 listings over here. If you are interested, you can see a report as well from the last option of this output, report. If you want, you can save this report from this save option as well. It just indicates how many azeotropes are formed, what are the compositions of those azeotropes, and what is the temperature corresponding to those azeotropes. So this is just a form, a report option. But the interesting feature is the last one, the ternary plot. The ternary plot. So the ternary plot takes to the second tab, the plot input. Previously we were in the Explorer. If you want to get back to the previous window, you can go to the Explorer, just immediate previous tab, or here we are in the plot input, that is the ternary diagram. All of you are looking at the similar curve. Okay, so we can play with this diagram as well. To play with these diagrams, we have a lot of options on the right. So what options are there? Let's first have a look on the option somewhere here where you have a rotate option, just below the triangle form. Here we can rotate the how we say, the vertices, yeah, three corners we can switch between, because this is the normal curve we see in the textbooks. So we are better used to this kind of the Ternary diagrams. Okay, another view is if you click on the equilateral one, then we can view this kind of diagram. So if you are more comfortable with this diagram, you can work with this, or if you are comfortable with the right angle triangle, then you can work with this. You can just click on this to switch between the two appearances. Okay, what we can see on this diagram. Are you familiar how to read this diagram, the Ternary diagram? You can also view the grids inside the Ternary diagram to better view where are the equal lines. You can just toggle the grid. The top corner is the ethanol, that indicates pure ethanol. The bottom left one is water, and the right one is ethyl acetate. The boiling points for these components at 1 bar are also listed. Then you can recognize 4 isotopes on the same window. The first one, that is very close to the ethanol at 78.12. Are you on the same window? So the temperatures are also mentioned on the corners as well. So pure ethanol boiling point is 78.31 degrees Celsius. Water is at 100.02 degrees Celsius. These are just the pure boiling points. It's not shown. Otherwise, on the left side you have a check box at the nearly at the bottom, BP temperature. If this is not checked, then you can check it to show this option. So if someone is viewing at a different window, let's say I had a look on this, then that green line was somewhere over here. If that's the case, then just mind the sequence how the components are displayed in the previous window, in the Explorer window. Just go to the previous Explorer, previous tab. On the input, just see the sequence of component 1, 2 and 3. Just make sure component 1 is ethanol, the second one water, and the third one is ethyl acetate. Yeah, okay. Now you can go to the plot input. Now you should have seen the similar curve. Done? Okay, great. Okay, so the azeotropic points are mentioned by their temperatures. 71.53, that is between water and ethanol. Then between ethyl acetate and ethanol is at 71.39. Personally, I don't like this blue envelope. Somehow it mixes with the blue lines as well. It's hard to read. So for that purpose, you can right click, go to this properties, and go to this envelope option. And the fourth option is the envelopes. And you can change the color of the envelope. You can choose any color of your interest. Personally, I like this light gray color. Okay. So now I can read this back. So what you can read from here, this whatever the color is, this envelope is the liquid equilibrium envelope, and the blue lines are the tie lines. That means any mixture in this phase will split into two phases. One phase will be on the left and other phase will be on the right of this tie line. Then we have out of this envelope we have the white area. This is a single phase region. There will be a pure liquid. Then the green line splits this complete triangle in 3 regions. You can notice this is one region, the second region over here, and the third region very close to the ethyl acetate. These are 3 regions that define the boundaries of the distillation process. So that means if you are in any of this region, you can do the distillation process, but you cannot cross the boundary to the other region. For example, If we have a mixture of ethanol and water anywhere in this bigger region, we can do the distillation, but the product of the distillation cannot be anywhere other than this region. They cannot be from this region, or even they cannot be from this region. So that mixture cannot be distilled in such a way we can get a composition more than 70% ethyl acetate. So that splits the distillation process. So we have the same information of the liquid liquid separation and the vapor liquid separation on the same right angle triangle. To read if we perform the distillation in any of the region, how to read what should be the distillate product composition and the reboiler product composition. For that purpose, you can use these tools. One of the tool is just add the tie lines, the first two options, add tie lines. Then the next two options are the add curves. These add curves are the residue curves, and the residue curves are for the distillation process. Let's say we can add a residue curve. You can choose it. When you click it, the cursor will change to this plus sign. That means that is selected, and you can drop anywhere in between any of the region. You can just click anywhere, and those will be added as the residue curves. Even this is hard to see. Let's change the color. Change the color again, go to the properties environment. These are the residue curves, and go to the second tab residue and change the color to your interest. Let's say I will choose this pinkish reddish whatever. Yeah, so these are the residue curves. Originally we have a mixture of equimolar composition. So let's say another residue curve with the equimolar composition. We can select the composition exactly for that option. Go to the fourth option on the right, add curves by values. Just use this option and introduce the compositions. These are the 3 mole fractions. Let's say we can use equimolar, cannot be exactly, but close to 0.333, and the fourth one is automatically detected 0.334, and just click OK. So we have added one of these curves. I believe that is this one. If you want to have more curves, you can just select that and click anywhere. Can you read the information from these residue curves? Let's say if we have a mix, let's first choose the point of the composition where we have to have. For that purpose, use the marker option. The fourth one, the sixth option, that is add a point as per your interest inside. So we have 0.33. You see a marker on one of the residue curves. Yeah, that residue curve exactly passes through that composition. That is the feed in our case. If we put this feed to a distillation process, can you just figure out what should be the distillate and what should be the reboiler product? There are the arrow curves, arrow options over the residue curve. So following the arrow, the same feed go to the right option, and that right option landed very close to the pure water ultimately. And if you follow back, that lands up to a 70.2 degrees Celsius azeotrope. So that azeotrope should be in the reboiler or in the condenser? In the condenser. That is 70.2 degrees Celsius. So if we distillate this product, we'll get product 1 in the condenser that will be azeotrope, ternary azeotrope, and you can exactly read that composition right from there. And the reboiler product will be at a higher temperature, that will be close to the pure water. So this is how we can read this residue curve. Depending upon what are the temperature profiles of the column, we can get any product over this residue curve. It can be pure azeotrope or it can be even less than the azeotrope right on the residue curve. So one option is we can do the distillation process, but from the distillation process we cannot go beyond this azeotropic composition, and the target is to reach to the pure ethyl acetate, that is on the other region. Let's first show the distillation process, and we can show the distillation process by a manual line. If you take a manual line, that is 7th option on the tools, and the left side should be on the somewhere on the curve. So far we don't know exactly where it should be, but anyway it should be on the residue curve, and the right option should be on the azeotropic composition, that is 70.21 degrees Celsius point. So that line connects the reboiler and the condenser composition, that is the distillation process. Okay, so once we are in the azeotrope, then we can add the solvent and move the azeotrope from its original composition to a new composition that lands in the two-phase region, and that region is the liquid-liquid equilibrium region. So for that purpose, we have to add the water to move this point inside the liquid-liquid envelope. So that point should be somewhere connecting this straight line between the 70.21 degrees Celsius point, ternary azeotropic point, and the corner. So we can rework and add some water. How much water should be? We can recalculate where we land on the two-phase region. Let's say we are somewhere over here. Just take this option, this 4th option, that is add marker, just to indicate where we land, and drop it somewhere over here on the line that is imaginary line as of now, but that line should be connecting the pure water and the azeotrope. That should be the straight line, and the marker should be somewhere over there. I can visually predict it should be somewhere over here. So let's say we add some water and we can land on this two-phase region, liquid-liquid region, and we can do the liquid-liquid extraction. We just give some residence time and take one product from the bottom phase and one product from the upper phase, and the composition of the two liquid-liquid products should be exactly on this tie line. You can drop a straight line as a tie line. So one product will be on the right of this envelope and one on the left on the envelope. What happened by just doing this exercise? Amazingly, we landed up in another liquid region. So initially we were in the left region, now we are in the bottom region, very close to the ethyl acetate, exactly at this point. Here we can do the distillation once again. Because we are in the same region, we want to get nearly pure ethyl acetate. In that region, we can put the product in the distillation column and get one product from the reboiler and the other from the condenser. But for that purpose, we cannot move from the residue curve. So you can add another residue curve, a random residue curve, take the 3rd option, just drop it on the product from the liquid-liquid extraction. So here you can add another product. So again, if we after first distillation, then liquid-liquid extraction, after adding more water, then we can have a second distillation process, and for the second distillation process you can get the product from the reboiler and the condenser. So let's say if we distillate this product, what maximum we can get? This residue curve, one side connects to the pure ethyl acetate and the other corner is exactly on the azeotrope. Yeah, all the lines converge on this same point, 70.21. So that line connects the composition of reboiler and the condenser. Can you predict what should be the component or the composition in the reboiler? a product having a high temperature on the same residue curve, that is 77.20 degrees Celsius, that product will leave from the reboiler, and the lower temperature 70.21 degrees Celsius, that will leave from the condenser. So we have successfully moved from one region on inside the distillation boundaries to another region, and split the complete separation process into three different processes: distillation, liquid extraction, and then the distillation once again. And what will happen with this azeotrope from the second distillation column? We'll mix it back before the liquid extraction process. We'll just recycle this stream. Conceptually, how it will happen in the flow sheet, I have provided in the handouts. So we have equimolar composition as a feed of the three components, put it into the distillation column, got one nearly rich water product from the reboiler, and the ternary azeotrope from the condenser. There is a mistake over here, we were adding water over here. So in this mixer we have to add water. So put more water over here, just move from this 70.21 point to this inside the envelope. Just make this correction. There should be a water stream entering this mixer as well. So mix water, then do the liquid extraction, get one product that is rich in aqueous phase, another product that is rich in the organic phase, and put that organic phase in the second distillation process, get nearly pure ethyl acetate from the reboiler, and recycle again the second distillation ternary product back to the mixer. So this is how we can rework, and using ternary analysis or the distillation synthesis analysis, we can work to get to a pure product, move from the azeotropic compositions. Just some minor makeups. If you want to remove any of the unwanted information from the left side, you can just check or uncheck options. If you are not interested in the distillation boundaries, then just ignore it. You want to ignore the residue curves, just move out of it, just uncheck that option. Don't like the tie lines, you can get rid of it. The plate point is 71.23 degrees Celsius. Can you just figure out where should be the plate point throughout this diagram? Where should it be? So in between the smallest one, still there is envelope, and at the very right corner inside those, that will be a point, and that will be a plate point. That means if we are talking about that composition, liquid extraction won't work for us, because we cannot anyway get the two products from the plate point. We have another exercise, it will take only 15 to 20 minutes, but this meanwhile you can play with this one. If you have any question, I can help you. You can try to do the analysis at, let's say, a different pressure. What should be the purpose? I don't know so far, but it can be helpful. Okay, then we have a last exercise for this day, and that is a solubility analysis. I suppose the file you have is missing some of the information in the solubility analysis. What this tool is, again the solubility is related to the dissolution of the solids and the solvents. We have one solute and one solvent, and we want to figure out at any given temperature pressure conditions how much that solute can be dissolved in the solvent. And these are very special cases if we are dealing with for example, the crystallization, because the crystallization starts when we have the saturated, how do we call, the saturated mixtures, and that saturation is not related to the humidity saturation, but this is about the solubility or the solutions. If we have more solute than it's the solubility limit, that means that is the perfect case to do the crystallization and get the solid out of the solution. Even one very common example of this solubility analysis when we are dealing with the pharmaceutical products. So which kind of drug is more appropriate to dissolve in which kind of solvent that is conveniently injected or administered for any medical conditions. So we can do the solubility analysis and figure out which pharmaceutical product can be dissolved in which kind of solvent, so much so we can have as injection or tablet or any other kind of drug, or figure out the convenient way to administer in the body. So these are two very common applications of the solubility analysis. But before solubility analysis, we need to figure out what kind of that solution formation is, whether it's simple physical solution formation or it's the ionic formation. If we have the salts, acids, bases, they makes the ions. Dealing with the ions is very different from just mixing sugar with the water. That is completely a physical process. So you need to mind the difference between whether we are dealing with the ionic solution formations or just a physical solubility of the solute in the solvent. Studying solubility for the physical process is quite simple. Let's take this another exercise, that is a salt, copper sulfate. Copper sulfate dissolves in water. In water in this case. We have some experimental data, and that indicates at different temperature what is the solubility limit. For example, at 40 degrees Celsius, what maximum we can dissolve is 285 grams of copper sulfate in 1 liter of water. That defines the solubility of this component. How to do this in terms of analysis? Let's get back to the simulation. You can either create a new environment or just replace the components. We don't need ethanol, get rid of it. For ethyl acetate, we have copper sulfate, CuSO4. You can delete the previous one. So we need two components. That means if you are working with the same file, you don't have to have the analysis anymore. Just see if you have any analysis thing over here, just delete it. This copper sulfate is a salt. It makes ions, and such systems are very special when we are simulating these systems. So in a physical state, when copper sulfate dissolves in the water, it's not CuSO4 anymore. It's not H2O anymore, at least in the solubility region. What are they? Copper ions, sulfate ions, ionize water in the hydroxyl and hydrogen or hydronium ions. These are the actual conditions inside the solution. So for that purpose, before even moving to the simulation, we have to exactly define the chemistry, what kind of components are formed. Those are the true components inside the solution. That is the electrolyte wizard, just an option below this component list, electrolyte wizard. Just before that, let's do the solubility analysis, then we can compare how it's different from simple physical mixing. Go to this solubility option in the analysis. Here is the window. You can locate this window. It's again in the folder analysis. We have two components. Which one is solute in this case? Copper sulfate. Move to the right, and on the right you have the option to the solvent. From the drop down in the component, just choose water. And for the solubility, if we are just dealing with how much mixing is there, it doesn't matter what flow rates you are giving. You can just take any random flow rate. So valid phases are vapor liquid, both. Solubility is inside the liquid phase, so keep it the same. Just notice on the right side, property method is NRDL HOC so far, and there is no chemistry ID. We'll come back to this, what is the chemistry ID. We can manipulate the temperature and see at different temperature what is the solubility of copper sulfate. So as of now, the temperature ranges between 0 and 100 at 1.01 bar. Just keep it the same. With the default conditions, we are ready to run the analysis. Just run the analysis. Okay. So this is what do we see? There is nothing in fact. So the analysis could not figure out how much copper sulfate dissolves in the water. Even let's say if we can go to the same solubility analysis tab and the third last option, that is the results tab, there is nothing displayed in this window. These are the numerical values of the actual results. So the Aspen Plus could not figure out the copper sulfate solubility in water. If you have a different physical solution formation, let's say you can put sugar into water, you can get the results right from here. But in this case, we don't have. But the problem is, when copper sulfate dissolves in water, it splits into the ionic formations, and that information is not available in Aspen Plus so far. We have to introduce that information. How to do that? Go back to the components and use this electrolyte wizard option. That is the wizard option. When we use it, it again searches the databases and gets the chemistry information of the electrolytes and choose wherever it requires. So click this option, another window pops up. Here the data source is given, that is the source where some reactions are listed, and Aspen Plus will search those reactions and figure out what kind of reactions should be fetched from there. Then there is a reference state, unsymmetric and symmetric. Unsymmetric reference state is normally used in the electrolyte solutions when we have water as a solvent. Symmetric is used when we don't have the water as a solvent, rather the salt is fused and get into the liquid form. That means it's higher than its melting point. So just mind this difference. We are using the unsymmetric option. Go to the next window. All components that should be involved in the electrolyte chemistry should be on the right side. So move copper sulfate to the right side. And below are the options. What kind of reactions do we want to fetch from the database? Salt formation reactions. Okay, if the solution is saturated, supersaturated, then should be salt formation reaction. Water dissociates, yes, check this option. And we are not interested in the ice formation in this case. Yeah, just choose the first two options. Go to the next window. And here in this window, it listed all the reactions that involve copper sulfate ions and the water ions. All the reactions, and those reactions you can see from the bottom window. These are all the reactions that involve somehow one way and the other react different components and different ions. Specifically, the salt components are listed on the top right window. If you see in your kind of system, you are not expecting in any of the salts, you can get rid of it. By getting rid of it, the relevant reactions will be taken away from the bottom window. But anyway, let's assume all these salts are possible. And at the bottom you have two options, electrolyte NRDL and electrolyte NRDL with RK method. RK method for the vapor phase and electrolyte NRDL for liquid phase. Somehow, to my experience, wherever I have used this feature, electrolyte NRDL method is more rigorous and almost provides a very closer information to the reality. And with the extension of RK, I have messed up with this method so many times, so I prefer not to use this one. So just use the first option. Go to the next window. We have a true component approach and apparent component approach. These are two different approaches that Aspen Plus uses, first to calculate different properties, and second to display the property results. So you can go to the next option with this, and that's it. Wizard is done. And with this, we are given options to review the Henry components, review the chemistry, or just finish it. Let's finish it. We can manually review those things. So finish it. Now you can notice there are so many other components added in the component list, and these are all the components that one way or the other involve in the solution chemistry. Somehow in this system none of the gas is formed, then it doesn't include that component in the Henry list, because the Henry component list is still empty. Otherwise it automatically, Electrolyte Wizard automatically moves the non-condensable gases to the Henry component list. Then see what other information are there to review. First let's have a look. The property method, we have changed it. Previously it was electrolyte NRTL HOC. Now we have changed it to electrolyte NRTL. It asks us to review this information. Let's have a look. Then particularly for the ions, some electrolyte pairs are formed where different energy values are given. Let's click one by one all of these, or you can move from next to next to next. It will, this is just information to review. We don't have to do anything, but just review. If you have a more realistic numbers over here, then you can replace these numbers. Otherwise we can live with this. Okay, just reviewing all these things. Still input changed gray, and we are ready to run the simulation. Let's go back to the inputs, the same solubility, and now you can run the simulation. But before running the simulation, look at the property method. Now it's electrolyte NRTL, that is updated, and we have the chemistry ID as global. You can have a look on the chemistry ID. If you go to this navigation pane under the folder chemistry, let's from the left arrow button expand it. There is a global folder. Further expand it. There is an input form, and just go to the input form. And you see these are the reactions. These are 3 and 5. These are 8 reactions fetched from some database related to the electrolytes. Even you can scroll other tabs, at least one tab that is equilibrium constant. Quite possible some of the equilibrium constant values are also given. Yeah, for one reaction equilibrium constant values are given. For the remaining it can get from the Gibbs energy. It can get equilibrium constant from the Gibbs energy. Okay, anyway this is just for the information, you can review it. But let's get back to the solubility analysis once again and run this analysis once again. Now we are ready to run this analysis. You see now we have the curve. This is a solubility curve where we have a temperature on the x-axis and some liquid SOLUB solubility, some fraction value on the y-axis. What those fraction values are, go back to the again the solubility input form, and you can have a look on the results. On the results tab, you have all the numerical values of that curve over here, and here we have multiple results. Unfortunately they are listed with the alias as solub C. What are those? That's also given in the help, but I have just taken a snapshot from the help. What are those? If we are with the W, that means we are talking about the mass basis, and if we have other than W, that means we are talking about the mole basis. One thing is the mole base and the mass base. Inside the mass basis, uh, we have differentiation with the single S at the start and double S at the start, SOLUB and double SOLUB. The double is amount of solute per amount of solution, amount of solute per volume of the solution. That means we are talking about the solution, complete solution. With the single S, that is amount of solute per amount of solute free solution. That means you got it. With the double, we are talking about the complete solution including the solute and the solvent, but with the single we are talking about the solution free of the solute. So now you can figure out, let's say this mole basis, what were the results with us? Okay, that was on the base of mass. We need to run the simulation once again and switch the basis from mole to mass for comparison purposes. Just change the solvent composition units and just do the analysis. Okay, now have a look from the numerical results, and from the numerical results now we have the values in terms of grams per liter. So this second last column is amount of solute per liter of the solute free solution. So that means we are literally talking about milligrams of copper sulfate per liter of water. So if you want to compare with the numerical results, and let's see if we are even close to the experimental value, just take any temperature. What temperature we can compare? Let's say 40 degree. Again 285 grams per liter is the solubility, and over here we are talking about 337 grams per liter. 337 grams per liter, and here we were having 285. So that means there is a mismatch. Yeah, there is a clear mismatch between the experimental values and these are the simulated values. What could be the possibility? The reaction chemistry have to be reviewed. Given the more refined results, maybe some of the salts even are not formed at these conditions. We can get rid of those salts. That is one possibility. Other possibility is electrolyte NRTL method is not appropriate to simulate this solubility data. Maybe we can switch from NRTL to electrolyte NRTL RK method. That is another possibility. Another possibility is we had the binding direction parameters. They are not displayed over here. Let's say if they are displayed in any other window. In one window, ions interaction parameters are given. Maybe we need to correct them. You can play with the results if different sources are available. What other possibility is how energy interactions happen between different ions, and those are given under the electrolyte pairs. Again, these are the values fetched from somewhere, whether those information is reliable or not. So having a different solubility data from the experimental values, there are so many reasons to have the wrong numbers, but at least we figured out how to do the analysis. So this is the way to determine the solubility, and you can apply this solubility to, let's say, crystallization process. So that the real lesson is, when doing crystallization process or doing the drugs delivery methods, that solubility data is the super important. You have to review it first, just like doing the binary comparison between vapor liquid experimental and vapor liquid simulated, to ensure if we are talking about the right method for the given system. So that is about solubility analysis. Just a very last quick another option that we can play with. There is a one feature under the property sets. Property set. And simultaneously in the analysis there is an option of mixture analysis. These two options go along. So wherever we want to have the mixture analysis, and mixture analysis is not restricted to only 2 or 3 components, we can have a list of all available components in the mixture, and we can do the analysis. And to do that analysis we can just create a new property set. The window will pop up with the question what kind of property analysis we want to do for the mixture. One option is you can pick the required property from the drop down under the physical properties window, and there is a very long list. We can do all this analysis with any kind of systems, at least the relevant systems. But these are all the alias digits. The real strength is in the search option. Go to the search option, and here you can search. Let's say if you are interested in analyzing the density of this ternary mixture, or if you have the list of 40, 50 or 60 components from the refinery, you are interested in analyzing the density of that system or the specific gravity of the system, or maybe you can just scroll down and have a look. You can analyze all these properties. You can get the boiling point, viscosity, refractive index, some compositions, even you can analyze the fugacities, ratios of the Cp and Cv. These are all multiple options. Let's for the sake of argument search for density. Specifically for the density we have multiple options: standard liquid density, or density at whatever the given conditions are there, or even the other density options, mass based, mole based. Let's pick the second option, density of the mixture, and that's it. You can click OK. That means for the for the copper sulfate system we want to analyze the density, how it changes with the with variation of any component, and that variation can be with respect to pressure or temperature or mole fractions of copper sulfate or water. These are so many manipulated variables. Sometimes it asks to review the second option, qualify the second tab over here for some of the properties, and these qualifiers are mostly related to the phase. You can check the phase in that when it's required. Otherwise for so many other properties it's not even required to check the phase. So that's it. That means we have defined one of the property from the list of available of dozens of properties, and we want to analyze this. To do the analysis we can go to the mixture option on the top right option under the analysis, do the mixture analysis, and here we can pick the components. So which components should be involved in the system, and here we can define some appropriate composition. You can define, let's say, equimolar. Just define 1,1 flow rates for the both components. It will get to the equimolar composition. And you should see this PS1. Did you figure out what this PS1? This is exactly the same property set we had just created, PS1. That's the density of the mixture. If we really want to include the true components, ions in the analysis, then we can pick them. Otherwise we can leave this as of now. This is just for the sake of exercise. Just shift this from the available to the right. You can play with the manipulated variables, whether you want to analyze this property density with respect to temperature or some composition. What should be the parametric variable? Mostly it's a pressure, otherwise you can get to the vapor fraction, and with this you can just run the analysis. And that gives the density with respect to temperature. How to interpret this? Probably we are talking about the different phases. You can just predict moles per cubic centimeter. This is at a higher density level, this is at a lower density level. Probably we are talking about different phases. One could be the liquid, one could be the solvent, solid. There is a possibility before 45 degrees Celsius, whatever the composition we have selected, we are in the crystallization zone where crystals are formed, and those crystals are in the solid phase. We are under the solubility data as of now, but at least you have figured out how to analyze any other property of the mixture at variable temperature or variation in the composition. So that's it. If you have any question, then we can address, otherwise we are free. I'll try to upload this session as early as possible. Still, if you get in trouble, we can schedule, but to schedule any session on Thursday, I need to know before that. If you can indicate, we can schedule the session on Thursday at 5 p.m.